Alright guys, so I'm not here today, unfortunately. So I'm going to go over what you were supposed to learn in class as an activity, and I'm going to have to explain it directly, sadly. So we're going to be looking at transformations, which you may remember from geometry. We're going to do it when looking at absolute value graphs. Okay, so general form of the absolute value function. I would like you to write this particular form down. It's going to be used through the whole lesson. What I want you to pay attention to in today's lesson is not the nitty-gritty math. Don't worry about writing down all the tables when watching this video. Pay attention to what the tables do to the graph. All I care about is you understanding how to describe how the graph moves around by changing the A, the H, and the K value. Do not get hung up on the tables. They're not that important. Normally you've done this with a calculator, but sadly I wasn't able to be there to have you do this activity, so I had to do it this way. Just focus on how the graph moves and the names, okay? Pay attention to that. That's what's important. Okay, so the first thing we're going to look at is what we call a parent function. So this is a parent function. It's the one in green here, right? And it is created from this guy right here, the parent function. This is the original absolute value graph. It's before anything else happens to it, okay? Below it is what we call the child graph. When we start adding numbers to the equation, we start to move the graph around in different ways. And so therefore it is different from the parent, but it originally started at the parent's location. That's why we call it a child graph. So I'm going to show this idea mathematically to you, and then you'll see where it ends up on the graph, and we'll just talk about what's going on. So if I'm looking at y equals the absolute value of x, okay, if I look at it in terms of a table, an xy value table, we could pick the points off the graph itself. I'm just going to pick some basic x values like -2, -1, 0, 1, and 2. And I just picked them because it's kind of in the middle of the V shape, and so we'll get to kind of see how the graph moves. So given the parent function, if I want to know what the y value is, I could easily see it on the table, but I want to explain what the absolute value symbols do to a number. If I take -2, all right, and I plug it into an absolute value sign, it turns that number into a positive. So if I plug in a -1, it turns it into a positive. If I plug a 0 in, well, 0 doesn't have a sign, it's a neutral number, so it will give me 0. If I plug in a 1, it makes it 1, because absolute value signs are referring to the distance from 0, so it's always going to make a positive value no matter what. And so that's these points on the graph here. Well, that's what that table just did for us. Okay, so now I'm going to go ahead and I'm going to make another little table just so you can see where these things are coming from. And I'm going to now do the child function. Okay, so now I'm going to make a table for this. I am going to use the exact same x's as before. -2, -1, 0, 1, and 2. So if I take that number, -2, okay, starting off at the top of my table, and I plug in the -2 into the absolute value, we saw that the absolute value of -2 is +2. But I have this +2 right here. So 2 plus 2 is 4. And that's how I find the y value. So if I plot that point, -2, +4, that's one of the points. I'm going to do the same thing, but now I'm going to go ahead and use the next number in my table, -1. The absolute value of -1 is 1, but I add 2 to it, and so the y value for that is 3. And I'm going to plot it on the graph. You might start to notice what's happening on our graph, the location of the points in comparison to the parent function. I'm now going to plug a 0 into the absolute value. The absolute value of 0 is 0, but we add the 2. And so the y value is 2. And if I continue this, you may notice something happening. Those points always seem to be so many units away from the original ones. If I plug in the 1 now, the absolute value of 1 is 1, but I add 2, that gives me 3. So it's right here. And so the last one would naturally be right here if I'm trying to create that v again. And now I have the child function. This is called a translation. The reason why it's being called translation means shift or to slide. And so what this graph did, these points slid up, they shifted up. We call that translates. They translated up 2 units. 2 units. So if putting a plus 2 at the back of the equation moved the graph up 2 units, well, if I make that back number a -3, what do you logically think would happen? I'm simply now going to take each one of my points and now doing the opposite, it should go down 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. All of them are going to go down 3. So this back value, known as k, does 2 things for us. It translates the graph up and down. So where we had y equals a absolute value of x minus h plus k, the k, if positive, will translate up. And if it's a minus, it translates down. So that back value behind the absolute value sign will move the graph up and down. It moves all the points up and down based on whatever that number is. Okay, so now we're going to look at another type of translation, but now this time we are looking at the H translation. So that's when we have a number located right here behind the X, but inside the absolute value signs. So I'm going to rewrite the parent function. I have -2, -1, 0, 1, and 2. And I know the outcomes of these because we just did it in the last problem, so we don't need to show the math here. Okay, now I care about the child function. Now I'm going to do something a little weird, all right? I'm going to do something a little weird here. When I make my table, instead of putting down the x values, -2, -1, 0, 1, and 2, instead, I'm going to put down the y values instead. So 2, 1, 0, 1, and 2. And I want to figure out what in the world my x values are going to be. So to do that, I'm going to do a little bit of smart guessing here. So if I have the absolute value equation, y equals some number minus 2 has to equal a 2, okay? Because I got 2's here. So I know that 4 minus 2 is 2, and in the absolute value signs, I get an answer of 2. So I'm going to put a 4 here. Bear with me on this, all right? I'm going to do this again, but I have to figure out another number minus 2, but using the absolute value signs would give me a positive 2. Well, I know 0 minus 2 is -2, but those absolute value signs makes the number positive. So I know this needs to be 0. I'm then going to do this again. But now I'm going to go ahead and do that with the number ones. So I need to think of a number minus 2 with absolute value signs would give me a 1. I know 3 minus 2, that's 1. With absolute value signs, I get a 1, so I know I need a 3. There's another number that can get me a positive 1. I could do just the number 1. 1 minus 2 is negative 1. But in absolute value signs, it turns it into a positive 1, just like I see over here. Okay, well now I need to make a 0. So I need to think of what number minus 2 would equal 0. Well, I think you guys know that one. That is definitely a 2. 2 minus 2 is 0. And with absolute value signs, it's 0. All right, I made a little oopsie. My apologies. This right here is not going to be a 0 there. It's going to be the 2 that I wrote in. There we go. So now I'm going to graph this purple table that I've made. So I'm at 0, positive 2. I am at 1, 1. I'm at 2, comma 0, 3, comma 1, 4, comma 2. So if I go ahead and connect my points, making my absolute value graph, you notice this time the graph moved to the right. Moved to the right. So that's letting us know that when we have x minus a number, it moves the graph to the right. Moves our graph to the right. So it's going to translate right, in this case, 2 units. It moves every graph, every point 2 units. Well, you might ask, but it's a minus. Why is it going towards the positive numbers? Well, the reason is if we keep the y values the same, if I want them to be the same, well, I gotta think what's happening to x. Whatever I make x, it's being powered down by 2 units because it's x minus 2. So I have to use a bigger x to get the same y value as I did before. And that is why the graph shifts in the opposite direction. So you can see here, I had a 2 for the y and a 2 for the y. Originally, I could just plug a 2 in for the x, and I would get a 2 for the y. But now, since I have the child graph as x minus 2, I need to put a 4 in to be able to get the same y value of 2. I need a stronger x because it's always having a 2 units subtracted from it, which makes it go in the opposite direction. So if it's x minus 2 moves to the right, then we know if it's x plus 2, it should go in the other direction. So as a visual example, if I have a point here, I'll just mark them in green here, 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 and here. Well, now, since it's x plus 3, I'm going in the other direction. I'm going to go to the left 3 units. So this one's going to go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And so the graph moves to the left. So anytime inside the absolute value signs when we're dealing with h, if we have x minus h, we translates right. And if it is x plus h, we translate left. We go in the opposite direction when it comes to h. And that's always when it's inside those absolute value signs. Now we're going to talk about a. So a affects the graph in a different way. A is that value in front of the absolute value signs. So when we take a look at the parent function y equals absolute value of x, So you have -2, -1, 0, 1, and 2. And we already know what these y values are. You've seen them in all the other problems. So the question is really happening when I do the child graph, make a child table, what's happening? So keep in mind, this is 2 times the absolute value. When you have that number in front, it's referring to multiplication. So this time there's nothing inside the absolute value signs but x, so I can use the same x values as before. And now you may wonder, well, okay, how do I get my y values? No problem. We simply take the x values and we plug them in. So we have y equals 2 times the absolute value of -2. The absolute value of -2 is positive 2. Remember, it's going to turn it positive. Then we times it by the 2 in front, which gets us 4. Okay? We're going to do the same thing, but now with the -1. The absolute value of -1 is positive 1. Times it by 2, and we get a 2. Going to do the same thing with 0. The absolute value of 0 is 0 times 2 is going to give us 0. Then I have the absolute value of 1, which is 1, times 2, which is 2. And by that same math, this last one will be 4. So if I graph it, I'll have the points at these locations. Now, I'm going to go ahead and I'm going to put in another graph, but I'm not going to do the table. If I go ahead and make another child graph, but this time I do y equals 3 absolute value of x, the graph will look like this. And so if you look at the original parent graph, which is this big green one down here, if we increase it to a 2, it turns into this blue one. And then if we increase that number in front to a 3, it becomes this light green one. They start to become more narrow, more narrow. And that happens because we have made this value greater than 1. So what do we call this? This is called a vertical stretch. It is the stretching the graph vertically. That's why it's looking more and more narrow. So it's taking the top of the graph and pulling it upwards, therefore becoming narrow more quickly. And that occurs when the a value is greater than 1. The a value has to be greater than 1. So then if we look at what else a can do, let's take a look at this 0.5. So if I go once again with that original parent graph, I use those same points. All right. So if I go ahead and I do the child table, once again, nothing's inside the absolute value but the x, so I can leave my x values the way they are, and the y values are going to change. Once again, this is referring to multiplication, so this is 0.5 times the absolute value of x. So with any number that I put in, I'm multiplying it by a 0.5. So if I know what the absolute value for the y's are right here, 2, 1, 0, 1, 2, I'm really just timesing those numbers by 0.5. So I will do one as an example. So if I go ahead and do y equals 0.5 times the absolute value of -2, the absolute value of -2 is positive 2, times 0.5, which gives me 1. And I can do that for all of them. And when I do that math, what ends up happening is this. I will get these values. And I'm going to plot those points. So now I'm going to do another child function. Okay, I'm going to do another one. I'm going to make it y equals a 0.25 absolute value of x. And that graph would look something maybe about like this. So if our parent function is the green one, if I turn it into a 0.5, it turns into the blue one. Now if I do 0.25, which is an even smaller number, it turns into the red one. You can kind of see that the graph is being pressed down to the x-axis, trying to make it flat. That's called a vertical compression up here. Vertical compression. It's a vertical compression. Vertical compression when the a value is between 0 and 1. It's when it's between 0 and 1. Okay, the last transformation. If you make the a value a negative, let's see what happens there. I'm going to use the same table we've done for the parent function. We've seen this the entire time. Just going to write this down quick. Okay, the child function, once again, that does refer to multiplication there. Nothing's happening to the x values. All right, so I'm going to do one or two of the calculations so you can see it in the table. If I take my -2 and I plug it in, I have y equals -1 times the absolute value of -2. So the absolute value of -2 is +2, but then it gets multiplied by this -1, giving me -2. I can do the same thing with the -1. So the absolute value of -1 is +1. 1 times -1 is -1. And if I keep doing this, these are the values that I'm going to get. So if I plot it, if I plot those points, you can see the graph gets flipped upside down. The graph gets flipped upside down. We call this a reflection, as you can see at the top right here. It's called a reflection, and we have a reflection when the a value is less than 0. So basically, the a value is a negative. So this is just a summary of all the things we just talked about. Here, when we're talking about the translations, all right, your 4 different kinds, the way they are shifting with the correct symbols. Below is referring to what the a value does, the vertical stretch when the a is bigger than 1, the vertical compression when the a is between 0 and 1, and when a is a negative, so when a is less than 0, when a is less than 0, we call that a reflection. Okay, so this is not about doing any math. This is about describing what happens by knowing what each number does when you look at the child function. So we have a parent function, y equals the absolute value of x. It says describe the transformation of the child function, y equals absolute value x minus 1 plus 4. So we're just going to identify each part. We have y equals absolute value of x minus h plus k. That's essentially what we have here. That means this -1 come on, green. is referring to that negative h, and this 4 is referring to that k. So there's no a value here. We don't have a number in front at all, so we don't have to worry about a doing anything. So what is this? What's happening to this graph? Well, the k value tells us up and down, so we can say this translates up 4 units, and the h value, we have x minus 1, which means it does the opposite of what you think. So it translates to the right, it does the opposite, 1 unit. And we have now described the transformation from the parent to the child. And that is all that's being asked of you. Problem 2, or example 2. So you have the same parent graph as before, but now we have our equation look a little different, and they want us to describe the transformation. No problem. So once again, we have, y equals a absolute value x minus h. And so this right here is talking about our h value. Here, I'll just do this a little different, make it a little easier to see. All right, so this is referring to the h value, and that's referring, I'll use red, that is referring to the a value. So a does two things. You can see the number is a negative. That number is a negative, which means we have a reflection. Now, we also have a 1/2. So imagine that the negative sign and the 1/2 are two separate things for a moment. The negative means the graph turns upside down. The 1/2 tells us a vertical compression, because it is less than 1, but greater than 0. Once again, separate the negative sign from your mind from the number. All right, so now we have to talk about the h. The h is it says x plus 3. So we have plus 3 for h. We go the opposite direction. So instead of going to the right towards positive 3, we go the opposite direction. So we have, it translates left 3 units. Okay, last problem. So once again, describing a transformation that's happening. We have the 1.5 that's in front of the absolute value, so that's talking about a. We have a minus 3 behind the absolute value, that's our k. So we go ahead and we say, if this is 1.5, that's bigger than 1, which means the a value is giving us a vertical stretch. And then the k value, it's a minus 3. The graph moves down. That translates down 3 units. And that's just what I want you to get from this. Knowing how to describe the transformations.